So now in chapter 7, we're going to completely switch gears and we're going to talk about something called parametric equations. When you're looking at an XY coordinate plane, and if you describe something in terms of parametric equations, you're describing that usually because, not all the time, but usually because you're trying to represent some curve that isn't a function. And so we have a new variable we're going to talk about here. This is called t. Usually it's called t because we're talking about it in terms of time. And so x and y now, our coordinates of x and y are going to depend on t. So x and y are going to be defined like functions in terms of t. And so then x and y are going to be traced out or graphed based on t as t increases. Here's our official definition. If x and y are continuous functions of t on an interval I, then the equations x equals x of t and y equals y of t are called parametric equations, and t is called the parameter. So this describes some kind of curve in the xy plane, but it's just represented in a different way that we're not used to. So we're going to still have sets of points x, y, but we're going to obtain those values of x and y as t gets bigger and bigger. And then the graph of the parametric equation is called a parametric curve. So let's look at our first example. Okay, so we have parametric curves here. We have an x of t defined as t minus 1. We have a y of t defined as 2t plus 4, and we're going to say that t is going to be between -3 and 2 inclusive. Okay, so when we make, just like when we're plotting points with x's and y's, we're just going to add a third column called t. And so we want to make sure that we stick with the restriction that's given to us. So I want to plot points including -3 and 2 between -3 and 2. So here are those listed here. Then our x and y coordinates are going to depend on this value of t. So when t is -3, you plug in -3 here, and you get that x is -4. Then when you plug in -3 here, you're going to get that y is -2. And then you just go through and do that for each set of x's and y's for each t. Now, once you, let me try to make this a little bit smaller so that we can see the whole thing at once. Now, once we have our points, we can go ahead and graph. But one thing you got to make sure of is that since we're doing this with respect to t, we got to keep track as we're plotting the points, which direction we're plotting them, because we also have to indicate what's called an orientation or a direction. So when t is -3, we have the point -4, -2. So on the graph, I'm going to plot the point -4, -2. So that's right here when t is equal to 3, or -3. Then our next point would be -3, 0. So that would be here. Then our next point is -2, 2. So that would be here. And as I plot the points, I get this line. Now, as I plot the points, the line is being drawn this way. So I want to make sure when I plot these points that I'm putting an arrow to indicate the direction that these points are being drawn as t increases. And that's called the orientation. So that tells us what happens as t increases. Okay, let's look at another example of graphing parametric curve. Okay, we have our x defined by t squared minus 3. We have our y defined as 2t plus 1. And our t is going to go from -2 to 3 inclusive. So here's my t from -2 to 3 inclusive. And I'm going to plot out my points for x and y. Well, I plug in -2 here for x, I get out 1. Then when I plug in -2 to figure out what my y is, I get -3. And then when I go through and make that chart, as I plot points, I have to keep track of the direction that I'm plotting the points as t increases. So when t is -2, here's our first point. We're going to plot 1, -3. So here's 1, here's -3. There's our first point. Then -2, -1 is going to be right here. Then -3, +1 is going to be right here. That's when t is 0. Then -2, +3, that's going to be right here. And then I go ahead and finish those points. And notice, as I drew the curve and plotted my points, we were going in this direction, which is why we have arrows facing this, so we can see the direction of the curve as t increases. Now, here's a perfect example of a curve that is not a function, right? It doesn't pass the vertical line test. Let's do one more. In this one, we're doing x is 4 cosine and y is 4 sine. And we're doing this for t is 0 to 2 pi. So I'll let you look at this chart. I'm not going to go through defining each of these points. But when we plot them, let's look. Our first point, we're starting at 0. We're starting at t is equal to 0 here, and as t increases, we're going to go down this list and then continue it over here. So our first point would be 4, 0. So we're starting here at t is equal to 0. Then as we go through, we're going to start plotting points around the circle in this direction. And by the time we're done, we're going to have a full circle. And as we plotted them, we went counterclockwise. So we're drawing our arrows in this direction to show the orientation. Graph this on your graphing calculator. Just like you can switch modes from function to polar or from function to sequence, we can actually change our mode into parametric equations. So if you hit the mode button here, and when you go down, when you see function, this is how you're putting in what mode you're working in as far as graphs. If you go over to the second one, down to function, and then over, it says parametric. So hit enter on that. And now when we go into our y equals, we have this set up to enter our parametric curves. So here's our x. I'm going to use this as our example. I'm going to put in t squared minus 3. Now, because it's in parametric mode, when we hit our variable button, it's going to come up as t now instead of x. So I'm going to put in t squared minus 3. And for my y, I'm going to put in 2t plus 1. Now, to adjust our window, we now have to take t into consideration, not just x and y. So let's go to our window. So let's see, our t is going to go from -2 to 3. So I'm going to put my t min as -2 and my t max is 3. And right now, let's put it into step 1 because I want to show you something, but you can change the intervals here. For my x min, if we want to see this graph, let's put in, let's say -4. Oh, that's already there. And then for our x max, let's go out to 7. And let's do that on a scale of 1. And then for our y min, let's go from -4 down here up to 8 on a scale of 1. All right, now when I hit the graph button, you'll see this curve here. The only thing that I want to point out, notice how this doesn't look real smooth. That is because when I made my window, I made this in intervals of 1. When I hit the trace button, you'll see that down below it gives you your value of t and your x and y now. So if we start at the beginning, notice because I set my window to do steps of 1 for t, that means every time I trace, it's going to hop to each of those steps. So in other words, when I hit this arrow to trace, to go to the next point, it's going to hop from -2 to -1. There's going to be no in between, which is why it looks so rigid. So when I hit trace again, it's going to hop up to 0. It's skipping all the points in between because I told it to go by steps of 1. Now, if I go back to my window and I change this to say steps of 0.5, it's going to look more smooth. And then when I hit trace, it's going to do it in intervals of 0.5. So now it looks a little bit more smooth. So when I hit trace, I'm starting at -2 here. And when I trace, now the t is going in steps of a half. So the smaller steps I do for t, the more smooth that curve is and the more in between points I'm going to get. So just be aware of that when you're graphing it. If you do big steps, it's going to look more rigid. And one last thing I want to point out as far as using your graphing calculator, it doesn't show us the little arrows for our orientation on here. However, we can see what the orientation is when we trace. So when I use remember you have to hit the trace button to be able to do this. So hit the trace button, and then when you use your left and right arrows to trace through, and it goes from the smaller value of t to the bigger values of t, you can see which way those points are moving. So just watch how your t increases. So for example, if I was sitting here and I used the left button, notice here it says t is 3. So if I go this way, I'm decreasing. So that's not the right direction. So make sure that when you start at the first t and you use your right arrows to increase your value of t to see which way t is increasing, which way your orientation is. All right, so now we're going to look at how to go back and forth between these two forms. We're familiar with having it as y with respect to x, and now we're learning this new format that we have it in terms of parametric curves. So we're going to learn how to go back and forth between those two forms. So here we're going to start with having it in parametric form, and we're going to put it in xy form. So we have x defined as the square root of 2t plus 4. We have y defined as 2t plus 1, and our t is restricted from -2 to 6 inclusive. So basically what I want to do is I want to rewrite this, getting rid of our parameter so that we can have it all in terms of x and y. So I'm going to look at my x, and what I'm going to do is I'm going to solve the x for t. We're basically just going to use a substitution technique. I'm going to solve this equation for t. So I'm going to square both sides, subtract 4, and divide by 2. So I get t is x squared minus 4 over 2. Now that I have t in terms of x and I have t solved, I'm going to take this t and substitute it in here into my equation with y. So I'll get rid of that t in here and I'll have it in terms of x now. So I'm going to take this t here and plug it in here. So I have y is equal to 2 times t, which is now replaced with x squared minus 4 over 2, and then I have the plus 1. And then when I do a little bit of simplification, I get that y is equal to x squared minus 3. Now, here's something we have to be careful of. When we look at this, we see that it's a quadratic. Now, and when we think quadratics, we think polynomial, so that its domain is all real numbers. However, when you're dealing with parametric curves and you have a t that's restricted, you have to keep that in mind. Because your t is restricted, I'm only going to be able to get out certain values of x. So we want to make sure that when we graph this, it's not going to be for all real numbers because our t is restricted here. So if we want to truly graph this in terms of x and y, we have to stick to that restriction. So to find out what your values of x are, if I plug in t is -2 to figure out what my x is, I get 2 times -2, which is -4. and I end up with the square root of 0, which is 0. So when t is -2, I get that x is 0. Now, if I look at the maximum value of t, when t is 6, I get 2 times 6, which is 12. 12 plus 4 is 16, and I get the square root of 16 is 4. So, whoops, I meant that to be x squared is 16, so x is 4. So when t is 6, I get that x is 4. So we want to make sure when we graph this, we stick to the restricted domain between x is 0 and x is 4. And then, of course, as we graph those values, make sure that you're keeping track of the orientation as well. Now, if this was just less than, without including the endpoints, remember that you need to put an open circle that you're not including those points. So keep track of those restricted values so that it transfers correctly when you put it into your XY format. All right, looking at this example here, we have x is defined as 4 times cosine t, y is defined as 3 of cosine t, and t goes from 0 to 2 pi. So if we want to put this in terms of x and y, the first thing that I thought of doing was to use inverse cosine to solve for t and then plug that in for this t here. But then I realized I would run into a problem because if I have nested trig functions that involve inverses, then we're going to run into the issue of restricted domains that might not match with this. Because cosine and sine are not one-to-one functions, and that might cause an issue. So we can go about this a different way. Rather than doing inverse, I'm going to divide both sides by 4 here, and then for y, divide both sides by 3. So I get these two expressions. And then we can use the Pythagorean theorem. And so if I take cosine t squared plus sine t squared is equal to 1, I get this. So I take x over 4 squared, y over 3 squared is equal to 1 squared. So this is what I get when I plug it into Pythagorean theorem. And what we end up with is an ellipse that has a center 0, 0 because there's no shift. Remember, it might be a while since you've had this, but if there was a center other than 0 here, we would have in parentheses x minus some value and then have that quantity squared, or y minus some value quantity squared. Because there's no shift here, the center is going to be 0, 0. The major axis is going to be along the x-axis because this is the bigger value. And so from the center out is 4, right? Because remember, you take the square root of this number here. So the center out is 4, and then when you double it, you get the whole length. So the length of my axis is 8. This is just a quick review of ellipses. When I take the square root of this to find the length of from the center out for the minor axes, that's going to be 3 out this way and 3 out this way, which gives me a total length of the whole minor axes as 6. Now, if you want to verify that this is the graph, if you plot some points, remember we're going from 0 to 2 pi when we're looking at t. So I created my t, my x, and my y, and I just did the major points, the quarters, 0, pi over 2 pi, 3 pi over 2, and 2 pi. When I plugged in these values for t, these were the corresponding values that I got for x and y. And when you plot them, it starts here and it goes around like this. So that verifies that we have an ellipse. And our orientation here is counterclockwise. All right, so now we're going to be going in the other direction where we have it in terms, where we have the equation in terms of x and y, what we're familiar with, and we want to set it up in terms of parametric equations. So there's many ways that you can do this. One very common way to do this is this example right here, where you just let x be equal to t and then replace x with t in here. That's probably the easiest way. Um, but really, you could let X be anything you want as long as the restrictions are aligned. So for example, in this case here, I can plug in anything I want for X. I don't have any restrictions. So the domain for this is all real numbers. So I could let this be anything, and I'm not worried about what I plug in for T. However, if we had the case where, for example, if we had Y is equal to the square root of X, and we said let X be equal to T, where T could be anything, then potentially we could be getting negatives under the square root. So when you set up your equations in parametric form, make sure that you are restricting your T in such a way that you're getting values of X that can be plugged into the equation. So if this was the function Y equals the square root of X, and I set up X is equal to T, I would want to make sure that I state that T has to be greater than or equal to 0 so that we don't get any X's that are negative to plug in to the square root and get negatives under the square root. So make sure as you're setting this up that you're keeping those domains in mind. But other than that, you can really set it up any way that you want. So for example here, my favorite number is 5. So hey, let X be equal to 5T. Let's try that. And I'm not worried about domain restrictions here because I know I can plug anything in here for X. So whatever I plug in for T, I get out whatever I want for X, and I can plug it in here, and I'm not worried about any restrictions. And then what you would want to do is replace X in here with 5T so that you have your Y's in terms of T. So I replace X with 5T, so plug that in here. And then I have 2 times 5T squared, and then minus 3. So when I simplify this, I get 50T squared minus 3. So here are my parametric equations. If I wanted to make it 3T or 7T or negative 5T, it doesn't matter. You just make sure that the restrictions line up. So whatever I get out for X, I am able to plug it in here. All right, so in this last part of the lesson, I'm going to go through a couple of famous parametric curves. These are pretty commonly known. One is called a cycloid, and that's if you imagine that you take a truck tire and you get some white paint and you put a blob of white paint on the tire so that you could watch it and it stands out. You could watch it as the truck drives on a linear path. You could watch the spot move and trace its path. Well, if you do that, the shape or the path that that dot makes as it's traveling on the tire around on a linear path, this is the curve that it makes that I'm highlighting. Okay, and of course it keeps going and going, but that's called a cycloid. And then here's the general equation for the cycloid, and A is the radius of that circle. All right, now we also have something that's called a hypercycloid. And if you imagine that that tire that has the spot on it is put into a larger tire, like a tractor tire or something, and as that tire moves within the larger tire and you trace the path of that white dot on your tire, it makes this kind of a shape, this here. That's called a hypercycloid. And then here is the general parametric equations for a hypercycloid. Now, if we scroll down and look, depending on the values of these A's and B's, you can get different shapes. Just like when you're doing polar graphing and you're graphing, say, cosine 4 theta or cosine 5 theta, that number in front of the theta is going to determine how many petals that you get when you draw that cosine or sine rows. The same thing goes with these A's and B's and this formula here. Depending on what these values are here, you're going to get a different number of cusps and different shapes. And so these are labeled here so that it shows you what the shape is based on your values for A and B. So pretty interesting shapes here. but those are called hypercycloids, and these are some pretty famous parametric curves.